Hi everyone, I'm Jared. Also work for Cisco Talos group here. Let's go ahead and get started. Maybe we won't. There we go. So just kind of a quick overview, who we are, what we do. I tend to follow myself in the detection research and vulnerability groups up there. Really just getting to kind of play with stuff, figure out how devices work, find out how to break them, and then try to find ways to help people, protect against those things that we find and the things that other people find. Lots of fun stuff. So the stuff we're going to talk about today really stems from two major places. The picture on the left there is a kegerator that one of my teammates built, actually most of the team before I got there, built using strictly ICS SCADA network equipment, except for the obvious kegerator stuff, with the intention of both for, the entertainment value, but also giving something for people to hack, to go play with, and get to play with some industrial protocols. So from that, I had some of the devices, some of the equipment inside of it is one of the ones that, the main one we're going to look at here today, which then also stemmed into one of my teammates, Patrick, a talk he did at DEF CON this year ago now, talking about a couple of things that I'll touch on here at the very, very end, that we, took a few steps further and made a lot cooler. So, I'm obviously not the first person to work on this, as I mentioned just a few minutes ago, but then there's also been a whole bunch of people outside of Talos who worked on it, did a whole bunch of cool stuff. So, props to them that gave me some stuff to look at, read, and go off of. So, this project here, we mainly had three main goals that we were looking at, and that we're going to talk about here today. Figuring out a way to remotely control a particular device, a programmable logic controller, to then take, once we have full control, to modify the configuration that is on that device to gain additional access that we are not supposed to have or that was configured to not let us have, and then take it even further and flash that device with firmware that we took from a default state, modified a little bit in the back end to kind of achieve what we wanted. So to start out, playing with the ICS Village and all that, I figure there's a few people in here who are familiar with a PLC before, but can I just show hands? Is anybody kind of familiar with what they are? Oh, all right, hell of a lot more than I thought it would. Cool. So then, as a chunk of it's really, at the end of the day, just a computer. It's got a different casing. It's a bit more hardened for, harsher conditions and all that. But at the end of the day, it's just a computer. It takes inputs, so whether those inputs are switches, buttons, what have you, and, does whatever logic you program inside of it and gives you outputs. So lights, mixers, anything you want. In particular, the one we're going to focus on today, the device I'm sure you've seen me fumbling around with up here, is the one up on the screen, the Micrologix 1400, made by Alan Bradley, Rockwell Automation, same group. That's kind of, it's an interesting one, and it's kind of helpful for demos like this and us to play with, because it's a whole lot more compact than most PLCs. Everything is all in one container, I suppose is a better way to put that. We don't need extra modules for our inputs. We don't need extra modules for the outputs. We have the nice little screen on there, which can change some configurations from there. It's going to be really helpful for the demo later, because I don't need to pull up all kinds of fancy programming softwares. We can just show it straight on the device. From Alan Bradley, the types of uses that it's there, it's mainly in smaller environments, hence the name Micro. So just to get a couple base things out of the way so that whenever I'm talking through this, anybody who's not familiar with this whole world, devices, PLCs tend to have something called key switch states, or at least what I'm calling key switch states. It's essentially just different modes of access that are often changed through physical controls on the device. Sometimes, and normally, at least in the ones I've seen, it's a physical key that you go and you turn it from run, remote, program, whatever you want. In this particular device's case, there's no physical key. It's just a menu, and then you switch the states across the three you can see up there. Program is kind of, what you'd think. It's a programming state. You have a whole lot more control over, what gets configured on the device, all that fun stuff. But nothing is running while it's going on. So, if you have it such that you flick a switch and the light comes on, that's not happening in program state. Then on the other side there, you have run state, which, again, pretty obvious. If you flick your switch, the light does come on there. However, you don't have, or at least you're not supposed to have, control over programming a lot of the stuff. So that's where we meld into the remote mode in the middle, which is the fun, more interesting one, because it gives access to the outside world, and it also gives a tiny bit, some other substates that you can play with and see, and it's largely what we're going to focus on for this attack, just because of some requirements across it, but we got some fun stuff with run too. In this device's case, the communication protocol used is Ethernet IP, and then within that, a application layer command structure called PCCC. For those of you not familiar with it before, it stands for the stuff up there. It's a fairly simple in of itself, just a little structure of command transaction value, a function code, and then data. So this here is just the simple case. We're going to expand later for individual commands. But largely the blue ones stay the same. Data changes based on, if you're trying to do a read, if you're trying to do a write, what have you. So looking through this, if anybody else is digging into this stuff in the coming future, these three documents there, one of them from the manufacturer, but the other two seem to be just specifications for the protocol. Really useful. So with all that out of the way, this is the base device configuration that we're going to start on to go through our attack here. Taking the device in front of me, the 1400 Series B, with the default SNMP state disabled. That's important. That's one of the big things we're going to focus on here as a demo, I suppose. And a firmware version of 21.003 or below. At the time we were working on this, 21.003 was the most up to date, and they've patched since and fixed a lot of the stuff we're going to talk about here. Making it better as long as people are updating. And then the two states I'll call less default is the memory module. It's required to have a memory module. It doesn't come by default, so, It also needs to be installed without a special write protect feature, which is normal if you just plug it in. And the CPU state, as I mentioned before, in remote. So let's get into it. Just to start, first thing we're going to look at is enabling SNMP. It's really important because we're looking to flash a device with new firmware. The way this device works for flashing is leverages SNMP, so we can't actually get into the flashing state without it. So with that, it's disabled by default, but it does not have a key switch requirement in this case. It does if you're trying to do this through RSLogix, the normal programming software for the device, but it doesn't for the way we figured out how to do it. And then the things I mentioned before. So whenever we first look at this, trying to figure out how the service gets enabled and all that, figured the easiest, best, smartest move would be to go look at the normal programming software. So RSLogix, if you heard me talk about it. The picture you see up there on the left is what I'll be talking about as a channel configuration menu, in this case, file later. If you see in the top left corner, you'll have an SNMP server enabled button, or checkbox, what have you. Whenever that box is checked is when you're starting to get SNMP enabled. However, there's that little caveat down, 3/4 of the way down, that says power cycle is required before this can happen, which this is also reflected over on the picture of the LCD screen at the very bottom, showing that power cycle is required. So we can enable it, but in order for it to actually occur and let us use SNMP, the device has to be power cycled. So digging through, Wireshark, it was at first a pretty big pain. So then we started looking, what can we make it to do better? Wrote a Wireshark dissector for it, which is out there in the public now and can be used, and makes life a whole lot easier to look at this kind of stuff. So, like for example, the highlighted portion I have there is for the channel configuration file, what we were just talking about. And we were able to use this to dig deeper into the data and figure out further which bytes are important, which bytes are changing, and dive into it. But before we could actually do any of that, we had to find out what that data was. So this is where, if you remember earlier, I was talking about the base PCCC command. You take that, and expand it out into the breakout shown above. In this case, all the orange is the data. And we need to send 2 read commands in this case, one to grab the first OX50 bytes and another one to grab the second OX50 bytes, with that restriction just seeming to be a limitation of the device, of the protocol, something to deal with, but it wasn't very difficult as the sub-element number field exists for you to kind of make some changes there. So when we build all those commands up, we can send them back across in Wireshark, again watching what's going on, using the dissector to watch a little bit better. And you can see all of the highlighted portions there is everything that came out of this command. So all of that data is all the data that comes back once you get that, or once you send those commands. So this is the actual data contained within the channel configuration file. And the one we really want to focus on is the one on the right, the orange colored one there, which will break out into a little bit easier to see. This is the same view as before of the right-hand side, except on the very, very top, we have just the straight data, the same thing that was shown, highlighted in the screen before, with that extra byte highlighted a different color. This I'm going to be calling the protocol control byte, really just because it's a bit field that just contains, individual bits as service on and off state for each of the different services. As you can see in the very bottom graph, those are the ones we were able to figure out. Didn't really dig a whole ton more into the question mark ones just because we were very explicitly looking at SNMP. So we set that bit, combine it back up into a full byte and replace the byte highlighted in the original response. And in theory, we should have SNMP enabled once we send it back up to the device. But we ran into a bit of an error. We kept getting error responses every time we would send it, and weren't entirely sure why. At first figuring maybe we were just screwing something up, but looking back and forth between different iterations of the actual programming software to do it, the data itself was staying the same as long as we didn't manually change it, in that earlier menu. So it didn't really make sense. We kept digging further and found a couple bytes in particular that created issues, or rather that changed on a not as predictable basis. So now we have the first response, so the first half of the data we're worried about in the top graph, and the second half in the bottom. This data is, we want to look at it as one big unit, the whole way up until the dark gray portions. So we found out that the second set of orange is actually a CRC calculation performed across everything from top left corner of the top graph, the whole way just up until the CRC bytes. So once we figured out that, calculate our CRC16 across all of the new data and replace the old CRC bytes, we go ahead and use a similar command to the one we were talking about earlier to send it back up to the device and hope that it works. Which you can see here, again, in another Wireshark breakout. In this case, same thing we were just talking about here, just in a prettier view. So once we do that, you can check on the PLC, you could check, in the programming software if you have it, anything. You could even look, it gives you a successful response code. You can look there. You'll find out, and you should have the device in a state where SNMP is essentially queued to be enabled. Not fully enabled, like we talked about earlier, needs the power cycle. So next step was digging into finding a way to reboot the PLC in some capacity, which turned out to be a bit more of an issue, as there was no default way to do that, at least not accessible through normal activity. So again, reason we have to reboot is so we can enable SNMP, and there's no way to do it by default. Again, here there's no key switch requirement for us, so this just standing on its own could be run in run mode, but for the full exploit we need everything. So since we didn't really have any other standard ways, we just kind of thought we'd take a super simple fuzzing approach and just see if we could get it to crash. Since all we really need the device to do is reboot, if we could do that and somehow let that work, it would be great. Didn't really have a whole ton of hope for that to work, honestly, because we were just piping random data into it, and lo and behold, it eventually just kind of crashed, which was really cool. But it was a little difficult to reproduce at first because we were just piping a completely random stream of data in, and sometimes it would work, sometimes it wouldn't, and sometimes it would take 2 minutes, sometimes it would take an hour. Well, one of these times we finally got a good PCAP of it that, one of the times it took just a couple seconds, and I could finally narrow down the data to what you see here being the important stuff. It's 24 bytes. All the nulls in this case really don't matter. It's specifically the E8FF that when you send this, and it's just TCP data, this isn't contained in any kind of special protocol. You send this to the device, and it crashes. Kept digging into that a little bit more, and found the fun situation where it didn't even need to be just those 24 bytes. If you sent any amount of groups of 24 bytes, so that's what the blue and yellow signify up there. As long as you send any amount of 24 bytes before it, all nulls, it will still crash, which was kind of cool. And interesting, certainly made us happy, since that's what we were going for. And it left us with a bit of a problem, though, because, so here you can see our SNMP queued, like we were talking about. We send our crash, and then on the far right, you'll see that SNMP is now disabled again, which isn't good. We kind of took a step back now, and it cleared our configuration whenever the crash occurred. So we need to find out kind of what was happening here, dug a little bit more into the spec sheets for what it is, and found out it was causing this error code 2 unexpected crash or unexpected reboot error. And whenever this error is encountered or gets triggered, what have you, it goes and loads something called the default program. So we didn't really know what this was at first. It was pretty clear that it completely overwrote all of the ladder logic that you had, all of the configuration settings, largely everything, and left you in a state where you'd essentially have to reflash the program, re-download upload the program to the device, and go from there. So we couldn't really find any way to mess with the default program itself, largely because we didn't really know where it was. But we found a more interesting option in leveraging a memory module. So within the configuration of this device, it was possible to set a memory module and download your program to that memory module. And then whenever a crash or an error, anything that happened that would normally load the default program occurs, you can now have the memory module pull from there. So it gave us a bit more interesting of a way because we could control that now. As we saw earlier, we're able to write and make changes to the program. Now we can store them somewhere, and store them somewhere that's better for the crash. So bought a memory module, started digging into how they work, and this is where the remote requirement comes in, mainly because it requires that we go through something that I'm going to refer to here as the programming routine. It's really just a sequence of commands that need to be sent before and then also after any of your desired commands, so that you gain the appropriate privileges and everything before continuing on and trying to run any commands. So in order to set this bit and let us progress and load from a memory module, we have to send a command similar to the one that we were discussing earlier to write. It's called information back up to the channel configuration. So in this case, we just change, they're not highlighted here, but the file number and file type have been modified to reflect more appropriately the files that we're working with here, in this case the status file. And then also some configuration data to ensure that the correct bit is set. Since we're overwriting and crashing everything, this example just destroys everything that would have been in the particular byte that it's working with. But normally you can do some math and set the correct bit and all the fun stuff for a real one. But then once you have that command all built up, if you were to just try and send it, it's going to fail because you need to run through this programming routine here. As you can see, the 3 commands in the beginning, essentially it's just putting into a program mode. This is where remote really comes in, because you can't send execute command list or get edit resource successfully. You obviously could just send them, but you need to be able to send them successfully and get edit access on the device before you could continue and send the commands you want, and then apply everything at the very end and return the edit resource so that things don't get all out of whack. Whenever you do this, if everything's successful and works just fine, you can look at it in the what's called the programming software in the status file and check out this byte, make sure it's set. If everything's good there, or you look at the status responses, can continue on and go ahead. But we can't crash it just yet because all we did was make configuration changes to make sure the device will boot like that in the future. We still need to store it to the memory module. So again, can send the command up above here. This will take the entire online program and store it onto our memory module for use later on. So just to kind of recap that a little quickly before we move on to the firmware stuff. Take a patch device, modify its channel configuration file, enable the device itself to load from its memory module whenever an error occurs. Take all of that online program now and store it to the memory module, crash the device, and whenever it all comes back up, as long as everything worked, SNMP will be completely enabled and fully functional. So with SNMP enabled, I'm going to move on to the real reason we were even looking at the protocol was to flash new firmware onto the device. So to do this, we essentially for time requirements, for really a means to an end here, we took and modified one of the existing firmware files at the time. So just snagged it from the vendor's website, pulled it down, and this is some slides and a work that one of my teammates did, and pulled and took what's the text for remote, changed that to hacked, which is what we're going to show you later, and then just had to make some offsets later. We were able to do this because the whole file, or at least the portion of the file we're working with here, just is operating under a normal checksum. So as long as all of the bytes add up to the correct end value, then it's good. So as long as we took all the changes from remote down to hacked and made those same changes, if you look at the very beginning of the yellow, you'll see one character has been changed, going from, I think, a capital D to a lowercase p. If you go to do the math on there, the changes all come to 0. And whenever you then go to flash it, it works beautifully. So to flash it, we leveraged a SNMP backdoor that had been found previously by Patrick, and then not patched. So this is still sitting in the devices. It's essentially a replicate of the private SNMP community string, but it can't be changed, which is unfortunate. But it gives you the same access, and you can use it to do different things. So while messing with the firmware update cycle, we found a way to reboot the device, which actually we found this one before the crash, so we were really excited at first, until the realization set in that we kind of loop in a circle here where we need SNMP to cause this crash, but need to cause the crash to enable SNMP. So obviously this one wouldn't work for our particular case, but I wanted to bring it up here just because, going forward, if SNMP is already enabled on the device for whatever reason, and you want to enable one of the different other services that was in that in the bit field that I was showing you earlier, it can be done like this. You don't need to go through the crashing. You don't need to use the memory module. A lot of the stuff we're going to talk about there won't need to be done if SNMP is already enabled due to this, which is rather nice. But once that is all set, SNMP is all enabled, we can go ahead and start with the firmware flashing. So you'll see 3 SNMP commands there, or at least SNMP set commands there. One to set the TFTP server IP address, one to set the firmware file name, and one just as the this crash that we were just talking about here. It's not really a crash, it just causes a reboot on the device. And that sets it up into the proper mode for pulling its firmware file from the TFTP server IP address that you specified. So here you'll see in the Wireshark printout there, it just pulling down through TFTP all of the file that we created down to the device, where it can then, if it passes all the checks and everything, go through a flashing process on the device and end up in a kind of final state with our modifications displayed on the screen itself. So, it's fun. I want to see a demo. Cool. All right, so this is that same PLC we've been talking about this whole time, and just kind of shown across a crappy little web camera. But you can read the important part. So check this out and make sure that it is running the firmware version that we were using at the time, so the most up-to-date one at the time, 21.3, and ensuring that SNMP is disabled, as you can see up there. Well, that looks nice. So we can go ahead and go through all the steps we were talking about earlier to try and enable SNMP. Or at least we could if I had connections. Yay. Explains a lot. Try this again. There we go. So now it's going through all the steps we were talking about earlier in that little flow chart to go ahead and update that channel configuration file, make all the updates, store that program, or I'm sorry, enable it to be able to pull from memory whenever we would crash the device, and then store that new program to memory. Once everything's set up there, come back in here and we see that SNMP is enabled, the nice blinking thing up top, and we have the power cycle button or display shown in the bottom. So if I were to crash it right now, well, since we've gone through all the process, it will work. Had we not already stored it to the memory module, it wouldn't. So do this, and you'll see the PLC itself. You saw the fault light start to flicker there. The device, essentially falls over and comes back up. And we're good. So, double check everything. Nope. Make sure everything worked. Yeah. So now we have SNMP enabled fully without any worries. We can actually interact with the device now. And we can flash the PLC with our custom firmware. Or, well, modified, I suppose. It's going to go through the same process. Essentially here, just waiting, and whenever you see the lights on the left start to change some more, it'll start pulling the file itself down from the TFTP server. That's what it's doing right now, before it starts actually flashing the device, which makes it really nice on this screen. And then once it's done flashing, it's going to essentially set itself to a reboot reset mode. Unfortunately, not one we could leverage for any of this. And then reset itself and come back up online. And if everything went well, display a little message up in the top right corner. Woohoo! Yay, now I don't need to use this. Ignore that. All right, so impact of all of this. I know it kind of seems like it was just a display change here that we, it seems like we could just gone in and changed a text file or something to read a different value. So it's important to remember where this change was occurring. Whenever we did this, it was a firmware level change. It wasn't just a slight modification. So you can take that to the next step if you have the time and the money and the interest to a point where you can make really whatever changes you want. So instead of a display change, you use the same idea to throw a backdoor in there somewhere. Or you take it even a step further, figure out how the checksum worked at a better level, and implement whatever you want in there. As long as you can get the device to accept the firmware, the process exists here to implement it. And all of that kind of brought me back to the quote you see up there, or at least the quote snippet, I suppose is a better word, from Reed Whiteman talking last year at S4 about the whole Trisis situation. And I realize it's different context, but the idea behind it kind of was interesting to me, that in this kind of case you can no longer trust the device anymore because of the potential for anybody to do whatever they want once they have access at that level. Just a little unnerving. So fixing it, what can we do to kind of protect against this and move forward with our lives? Main thing is really network segmentation. Kind of as you would think, these types of devices often don't need to talk to Google. They're in environments that can be segmented and pulled off in ways that would make it a whole lot harder to get access to them. Kind of continuing on that line, making sure you're actively looking at what's going on and understanding, what your network looks like, your standard network monitoring stuff. Also, even though, I mentioned a couple times in here that there are things that can be run in the run key switch mode, it still is, a good idea, if possible, to put it into that mode, because you reduce the attack surface that much more. And then finally, make sure the firmware version is at least at 21.004, which is discussing protecting against a lot of the things that we talked about here, and especially all the things that were able to be done here in run mode. Such as these ones. So the two in orange are two of the ones that we discussed today. The three in blue are just other vulnerabilities we found through this project that didn't really pertain to the story here. But they were still able to be done in run mode, which has its obvious bad problem. So this is where, especially if you're going to put a memory module in there, would be suggested to enable a feature called write protect. If you remember from earlier, I said we can't have that on for this. That feature essentially will take your device, write whatever your program is to it, and then cut off write access, at least logical write access to it from there forward. So whenever I would go to run that store to memory module command discussed earlier, it wouldn't function. It just wouldn't work. At least ideally, as long as there's not an issue there. But and then additionally, if you're running Snort or any of those products, we have Snort rules available that you can enable to detect on and check out some of this stuff. So if you have interest in more details, any of that through the other vulns we found through here, or maybe a paper version of this talk, any of that kind of stuff, go ahead, check out all the stuff up there. If you were looking at this protocol, the Wireshark dissector is working its way through their process. It's you can find it in the dev build at the moment, but eventually it'll make its way to stable. But yeah, any questions?